In order to perform step 3 of the lateral load analysis process, we need to know where the lateral load resisting elements are. When we look at a plan view of a structural system, we are looking as if above it. To be able to communicate with other engineers, we label the system, numbers in one direction and letters in the other. We call these column lines rather than grid lines because they are not necessarily evenly spaced. Something important to know is that not all column lines are lateral load resisting. We typically need fewer elements to carry lateral load than to carry gravity load. So to perform analysis, we need to identify which of the column lines are lateral load resisting. Fortunately, there are only 3 types of lateral load resisting elements. If a structural frame has only pin connections and pin supports, there is no resistance to lateral load. Pushing sideways on this frame will result in the frame falling over. This is called kinematic instability. The pieces can move without changing shape. Adding rigid connection between a beam and column changes that. Consider this simple example. Remember that in an elevation view, pin connections are shown as hollow circles and rigid connections are shown as connected lines. As the top of the level moves with the loading, the left column is pinned at the connection and support, so it experiences rigid body motion. That is movement without changing shape. But the right column is rigidly attached to the beam. For that connection to move to the right, it needs to rotate, thus causing bending in both the beam and the column. Another simple example is this frame with pin connections but fixed supports. For the top to move right, the columns must bend. Both of these are examples of the lateral load resisting system called a rigid frame. We typically identify rigid frames in plan view by the rigid connection symbol between beam and column. For this example structure, column lines 1 and 3 are lateral load resisting in the left-right direction. Line 2 does not have any rigid connections in that direction, so column line 2 is not a rigid frame. Notice that we don't need all of the connections in the column line to be rigid in order for the line to be lateral load resisting. In the up-down direction, only line D has rigid connections, so only line D is a rigid frame. Another type of lateral load resisting element is braced frames. Braced frames use diagonal members to provide lateral stiffness. Common braced frame configurations are diagonally braced frames, which have one diagonal member in a bay, cross-braced frames, which have 2 crossing diagonal members in a bay, and chevron-braced frames. Chevron-braced frames use 2 diagonal members to make a downward-facing V shape within the bay. Inverted chevrons are upward-facing Vs. In plan view, braced frames are typically shown as closely spaced parallel lines to denote that there is a beam and at least one diagonal member. We add a 2-letter abbreviation for the configuration of the braced frame. DB stands for diagonally braced, XB stands for cross-braced, and CB stands for chevron braced. In our example structure, column line 1 has a chevron braced frame, and column line 3 has a diagonally braced frame. Column line 3 has both a rigid frame and a braced frame. The type of system is not as important as recognizing that column line 3 is lateral load resisting. There is a structural system called a diagrid that looks similar to a braced frame but is really a rigid frame. Braced frames all have horizontal members, so the system looks like triangles. When the system is made of quadrilaterals, it is called a diagrid. The diagrid requires rigid connections to make the frame stable, so it is actually a rigid frame. In some cases, we use a short diagonal member near the beam column connection. This lets us use pin connections between all the members, but the system behaves like a rigid connection. We call these knee braces. Since knee braces act like rigid connections, we characterize them as rigid frames rather than braced frames. But again, the key point is that they are lateral load resisting. The third type of lateral load resisting element is structural walls. An older term you might hear is shear walls. Structural walls are members with a really large aspect ratio. That means the width is much bigger than the thickness. They might be made of concrete, masonry, wood, or even steel. For our purposes, structural walls in a plan view will be shown as solid rectangles. For our example structure, there is one structural wall. It runs from A1 to A2 and makes column line A lateral load resisting. Structural walls are so thin, they have practically no stiffness in the out-of-plane direction. That means this structural wall does not help resist load in the left-right direction. It only has stiffness in the up-down direction.